A roller coaster consists of a car coming down a hill, then going through the loop, that has a radius of 25 meters. The design intends to have the rider experience weightlessness at the top of the loop. Calculate the velocity of the driver at the top of the loop, and calculate the height of the hill required to achieve this speed. Now, the term weightlessness means that the normal force acting on the driver is equal to 0. So let's just make a note of that. Fn is equal to 0 at the top of the loop. Okay, so since the car is turning, we know that the centripetal force makes the car turn. So since centripetal force makes the car turn, we need to figure out what that is, and we get that from the Freebody diagram. So we know at the top of the loop that we have mg pointing down, and since the car is upside down, so imagine like a chair and the person here like that, we know that the normal force is also going down. So we have Fn. But we said Fn is equal to 0. So this right here, that is the sum of the forces, and the sum of the forces is what provides the Fc. And in this case, Fc is merely equal to mg. Okay, that's it. It's that simple. So what we can do is we can figure out what the minimum speed is. So the minimum speed, we're going to use Newton's second law for circular motion. So Fc is provided by mg, and we have m, and AC is v squared over r. And we can see that the mass of the person doesn't matter. All people will experience weightlessness at the same time at the top of the loop. So v is going to be equal to gr quantity square root. So v is equal to square root of 9.81 times the radius. The radius is 25 in this case. So v is going to be equal to 16 meters per second. So that's what you need to make the driver at the top of the loop feel or achieve weightlessness. So the driver would achieve weightlessness at that particular speed. If you go slower than that, then the driver actually won't make it to the top of the hill, and then they will just return backwards. So now let's figure out the next part of the problem. B. It says calculate the height of the hill. Well, here we're going to have to go back to an older topic of conservation of energy. So we know that the initial energy is equal to the final energy. So the initial energy at the top of the hill, since we don't know if it's moving or not, we're going to assume that it starts from rest at this point. So that means that we have GPE initially, and that's all the energy that we have. That's a reasonable assumption unless we're told that the car is moving at that point. And then what happens is the car goes around this loop, so it achieves a different height. So it still has GPE, but it has a different height. And of course, the car is still moving, so it has kinetic energy, final. So let's fill out these formulas. We know GPE, the formula is mg, and in this case, capital H. That would be this GPE here. And then this right here, this would be the final position for the problem. That's going to be mg, let's call that H final, plus 1/2 mv final squared. So mass cancels, you see. So all the riders experience the same thing. And so G is 9.81. H is equal to 9.81. What's the H final? So H final right here, from here to here, we see that it's twice the radius. It's the diameter of the loop. So H final is going to be equal to 2R, which will be 2 times 25, which is 50 meters. So what we could do is we could put 50 meters here, plus 1/2, and the final velocity would be this right here. It would be the velocity at the top of the loop. So 16 and squared. So this is 9.81 H is equal to 9.81 times 50 is 491. And 16 squared times 1/2 is 128. So H works out to 63 meters.